All right. So we were just talking before I started the video because I forgot that vectors are a lot like array, but there's an ending point, so it doesn't go on forever. We use length, which is called magnitude, and we use direction to represent a vector. And that the last thing we were talking about was that vectors can have the same length and same magnitude and same direction, but like have a bunch of different starting points. So they're like all over the place. And then I said, have you ever seen them in real life? And then I was going to look it up. And then I thought that would be cool on the video. And then I remembered I wasn't recording. Okay. Yes. Gravitational. Let's see. Or gravitational field is a good thing to write. Maybe not. There's pictures that I know I've seen a million times that have all these vectors on it. This has vectors. I don't know if you guys can see this. I can't zoom in because of whatever they've done to my computer. I can't zoom in, but if you can possibly see, the vectors that are further away from the Earth have less magnitude, less strength. They're not as long. And there's another example. There's like some really cool pictures that have gravitational fields, but like in space. Oh, it's so cool. Maybe I should write vectors in it. And then I'll stop looking. Yeah, here, look at this. They've got a bunch of different vectors in there. Whoa, how about that? Vector fields, there we go. I know weather's going to use it. I know space and gravitational stuff is going to use it. So if you have any interest in going into those fields, you'll definitely be using a lot of vectors. Look how cool that is. It's got the moon and the sun, and I don't know what that is down there because I didn't click on it. Is that a rock? Is that a comet? What is that? Now, what is that? Yeah, but look at the cool. Okay, I'm done. I'm done playing. Sorry. Okay, go on. Vectors represented by directed line segments. Let bold face lowercase u, do you see how it's bold, be represented by the directed line segment from P to Q. V is going to be represented by the directed line segment from R to S. We're going to show that these two vectors are equal. They're equal if they have the same magnitude and the same direction. What is magnitude? Length. How do I find length when I have ordered pairs? Distance formula. Yeah, distance formula from so easy. Here's the distance formula, and then I want to talk about what the distance formula really is. If you don't know, which I hope you guys know, but the distance formula is x2 minus x1, and then square that, plus y2 minus y1, and then square that, and then add those together, and then take the square root of that. And that is a formula that we use all the time in math. We're going to use it so much. We've been using it. What formula is that besides the distance formula? Oh, no, we don't know. No, that's not that slope formula. The slope formula is like y2 minus y1 over. I know, they're related. They're definitely related. I know how to help you figure it out. With the slope formula, if we've got 2 points, if you need to find the slope between those, you would take the rise and the run. I didn't draw my line. Sorry. You would take the rise and the run. So that's the slope formula, the rise over the run. But if I wanted to know the distance between these, what formula am I using? What is it? Not the slope formula. Pythagorean theorem. This is the Pythagorean theorem. It's just like x squared plus y squared, add them together, then square root. It looks way more complicated because this is just dumbing it down so much by saying literally take the two x's and subtract them, then square them. Like it's dumbing it down. Where if you just look at the picture, you would have to subtract those x's to find the length of one of the sides and subtract the y's to find the length of one of those sides. Does it matter if I do x2 minus x1 or x1 minus x2? Why not?
As long as you keep them in the same order, like the x's and the y's, it should be okay.
For slope, you are correct for slope. But for the x's and the y's in distance formula, it doesn't matter what order I put them in because once I square them, they both become the same answer. If I'm doing like 5 minus 7 or 7 minus 5, I'm going to get 4 once I square it either way. So it really doesn't even matter the order. Just some fun things that I've picked up along the way that I think are time saving. Okay, now going back to what we're doing. We are trying to prove that these two vectors are equivalent. They did say that they are. We're going to do that by showing that they have the same magnitude in the same direction. So magnitude. We're going to show they have the same magnitude. And I'm going to use vector u first. And I'm going to use the symbol that means magnitude of u. And I could boldface u if you want me to. There we go. So I'm doing find the magnitude of u. And that's the distance formula. So I can plug it into my formula that I wrote where you can't see it anymore. I could plug that in. I'm going to get 3 minus 0 squared. Oops, did I do? No, I did it right. Plus 2 minus 0 squared, which is going to give me 3 squared plus 4 squared. No, I didn't get 4 squared. My bad. I was thinking too far in the future there. Sorry about that. I knew that was wrong as soon as I wrote it. So I got square root 13 for the magnitude of u. So we'll do the magnitude of v. And let's see, we'll be doing, what is it? 4 minus 1 squared plus 4 minus 2 squared, which is 3 squared plus 2 squared, which is square root 13. So we have the magnitudes being totally the same. Then we have to show that the direction is the same. So let's think, in math, when I talk about the direction, what's something you could totally tell me by looking at the picture, the direction of u and v? One thing you could tell me. It's going up. Yes. So I know for sure by just looking at it that they're both positive. That's not enough information to say that they have the same direction, because if one of them's going up like this and one of them's going up like that, then they are not the same direction. But we are going to use the slope. Exactly. There you go. You knew you wanted the slope so bad. You were just waiting for it to pop up. Actually, what we're going to get to on a different page is really, when we talk about direction, we'll end up finding the directional angle. Like we'll find a theta. And what do you think we're going to need to find that theta? Something, I don't know, that we've been studying for a while. It has to have triangles, but it's not always triangles, but trigonometry. We're going to be using trigonometry again. Yes, can't get enough of it, right? Chapter 6 is full of trigonometry still. So we will be still be using trigonometry to find that directional angle. Now for the second, what am I saying up here? Vector. Like it would have to be a directional angle from horizontal, because that's what I did my pink one. I did both of them from horizontal. So we would need the same direction, but it's not asking for the angle. So the slope will give me the same thing. The slope's going to give me the same thing. So let's find the slope of each line. So the direction, we'll just do slope of u, thick u, So I could use my formula, or you might be able to do rise or run really fast there. What is it? 2/3. The 2/3, we're talking about going up 2 over 3. That number, those numbers with the 2 and a 3, because Evan really wanted to talk about the slope when I was doing distance formula. The numbers are in there too. So you're going to see the 2 and the 3 from our distance formula, because that's the change in the x's and the change in the y's. So how about the m of vector v? 2 over 3. And again, we could subtract those numbers, plug it into the slope formula. You can also look right here, because we already subtracted those numbers. So it's convenient. We already did that. So now we've got the same magnitude, the same direction. I guess the only other thing would be to say that they're both starting on the left and going to the right where the arrow is pointing. Like the initial point and the terminal point is going to be the same for both of them. Because if one of them had the arrow the other way, they wouldn't be the same direction. And that's where the directional angle is going to come in handy eventually. Okay? Next, component form of a vector. Again, a lot of vocabulary. Component form of a vector, we are going to take, and it's written down below, but I'm just going to write it up here as I'm talking about it. We're going to take a horizontal change and comma a vertical change. And we're going to put it in chevrons, those little greater than, less than symbol kind of things. Those are called chevrons. So we're going to put the horizontal change, comma the vertical change, and that's from the starting point to the initial point to the terminal point, from the starting to the end. Okay? And you know what that is? Just draw like a vector over here. The horizontal change is subtracting the x's. And the vertical change is subtracting the y's. I ran out of space up in that corner, but I wrote y2 minus y1. I wrote x2 minus x1. That's the horizontal change. That's the vertical change. So this formula I could rewrite if I want as x2 minus x1, comma, y2 minus y1. This is the component form for a vector. They called the x2 minus x1 v1 and the y2 minus y1 v2, because we're going to use those v's in other places. So they just simplified it, and instead of keeping it x2 minus x1, they just called it v1 and v2. Now, in their box, I think it got way more complicated, because they were using the initial point P and calling the x P1 and calling the y P2. And I feel like that was way more complicated than using the x2, x1. So I wanted to put my version of it up there instead of theirs, but it's the exact same thing. It's just different letters. I use x sub 2 to represent the second point, to represent that terminal point. So does it matter? Could I do x1 minus x2 instead? Does that matter? I can go back to this one. Does it matter if we do x2 minus x1, x1 minus x2 instead of x2 minus x1? Let's look at the one that has super easy numbers before you all tell me the wrong answer like you already did. From P to Q, if I'm just thinking horizontally, what am I doing from P to Q? Only horizontally. We're going to the right 3. So this component form is going to be 3, comma. What am I doing from P to Q vertically? We're going up 2. So that's going to be comma 2. That's the component form of U. Does it matter if I did 3 minus 0, 2 minus 0 versus 0 minus 3, 0, minus 2. It would matter because if I did the second one, that would tell me I'm going from my initial point left 3 and down 2. Or that would tell me I'm starting at Q, which I'm not starting at Q. Okay, so the order does matter for these. With the slope, it didn't matter as long as you switch them both. With distance formula, it doesn't matter at all. It does matter with vectors because of that directional component. Okay. There is something called a 0 vector, which is denoted by 0, 0. That would mean it has no direction and no length, so nothing's really happening. And then there is a, is it down? Where is the other one? Oh, maybe it's lower. Oh, here it is. And there's something called a unit vector where the magnitude of the vector, what's the magnitude mean? The length of the vector is 1. And remember when we did unit circle, the length of the radius was 1. So if we do a unit vector, it's probably going back to using it something with trigonometry, probably. Because at that point, we're talking about unit vector, the length of it is 1. And I don't know, you ever seen a unit circle have something like an arrow on it? And that's the radius. Right, so the vector is 1, the unit circle, the radius of 1, it's all related. Okay, we're going to find the component form. Why don't you guys take a moment and see if you can find the component form. I showed you how to do that. Then we'll do the magnitude together. I didn't go over the magnitude. We did, but we didn't. So see if you can find the component form. I'm going to do it up here. Don't look till you're done. So I hope that was enough time to do the component form. You subtract x2 minus x1, negative 5. Subtract y2 minus y1, 12. Questions? Second thing is the magnitude. So I'm going to use my symbols so we start remembering them. The magnitude is the difference, distance formula. We already found the distance between the x's and the y's. We already found it when we did component form. So now we just have to take that v1, which is negative 5, and square it, plus the v2, which is 12, and square it. And gosh, I don't even have to do work because that's a triple. What is it? 13. So knowing those triples save you some time too. My magnitude is 13. It does not say to do this, but let's graph this vector. It says our initial point is at 4, negative 7. I'm just going to sketch it. I didn't give you like anything to do it on, so. And then our terminal point is at negative 1, 5. So when I graph my vector, I don't know if you can see there's an arrow. I'll darken it. When I graph my vector, I can see the direction it's going. I see how long it's going. And using the component form, if I go from the initial point and I go negative 5, and then I go up 12, then I should end at that terminal point. All right, and then that would mean my hypotenuse is 13, or my magnitude is 13. Are we doing okay so far? Shouldn't be anything challenging yet. Now, we're going to add together vectors, and we're going to do scalar multiplication. And if I were going to give you a question and said, add these vectors or do a scalar multiply, I bet you just guess it right the first time. It's pretty like intuitively what you would think it is. So to add vectors, we have to add their same components. We're going to add the two x's together. They used u and v, but we're going to add the two x's together, and then we'll add the two y parts together, and that will be our sum. So it's exactly what I think you would probably do if I told you to like guess. And then another thing that if I just told you to guess, if we were doing a scalar where you've got a number multiplied by the vector, here they've got a k, I think most of you would be like, do I just distribute it? Yeah, that's what you do. You just distribute it to the two numbers and we get k times the x and k times the y. So those are pretty easy. They're, like I said, like common sense, I think. Some of this stuff is not common sense. That's common sense. Now, here's some pictures of vector operations. And this is where things tend to sometimes get a little confusing, is the pictures. So we've got vector u and vector v. You've got two vectors here. There's no numbers. Vector u and vector v. I'm going to go ahead and just like highlight vector u and highlight vector v. If we add u plus v, then we would go to vector u, which is right here. And then at the very end of vector u, we would attach on the same length, which is magnitude, and the same direction, just right on the end of that. So even though vector v was originally here, if I add them together, we're doing length and direction of u, and now length and direction of v. So we've got a u and a v, but that's not the answer. The answer is vector u plus v, which I'm going to show in green. It's going to have that same starting point, and then the same very final terminal point after I've added them together. That's the vector u plus v. So it keeps the same starting point. It keeps that other end point when I put them next to each other. Yes, Evan.
Is there anything different if you do vector v plus u?
So vector v plus u would look like, let's see, I did u. So that would be like me putting u right here. Okay. And then there would be v plus u. Now, it has a different starting point, but if I'm only talking about vectors being recognized by their size and their direction, those two are equivalent. Both of the green ones are completely equivalent vectors. If we're talking about size and direction, totally the same answer. So if we're only talking about the vector itself, it's the same answer to do it u plus v or v plus u, even though the picture might look a little different because of my starting point. Okay. Over here, the starting point doesn't really matter. What they've done is they've drawn these dashed lines so you can just have a concept of length without having to give you numbers. So vector v is our just initial vector there, and then they did a scalar of a half. So you can see that it doesn't affect the direction. It only changes how long it is. All right. Don't worry about where it starts. It just doesn't affect the direction. It only changes how long it is. The next one, 2v, doesn't affect the direction. It changes how long it is. Negative v changes the direction. Doesn't change how long it is. Just changes the direction, not the magnitude. And then negative 3/2 v is going to make it 1.5 as long, but negative makes it go the other direction. Okay? Those are just some examples of what scalars do to vectors. And then down here is showing you that subtracting vector v is exactly the same as adding a negative vector v. So let's see, u plus v, where's my u? My u is, so I was going to mark it. My u is this guy, and then my v is this one. So if I do u take away v, that would be Oh, I didn't mean to make that green. Hold on. I got to do my colors that are mixed together. So if you do U take away V, then that one ends up being this green one here. So if I go to U, but then I do negative V, that's going to be the green one. But if I do U plus a negative V, oh no, that's the same thing. Hold on a second. Now I got to remember what I said last time. Now I can't think. I can't think at all. But they are the same. And that's kind of saying what Evan's question was. Okay, so here we have some vector operations. We're going to answer these operations. And then are the graphs done? Yeah, the graphs are done. We'll look at the graphs afterwards. So 2V. So I've got a vector in component form. I don't have its endpoints, so it doesn't matter where it is. I've got vector V that says negative 2, 5. That means from start to finish, we go left 2, up 5. I don't care where the start is. Okay, so we're going to do twice that. So you're just going to do, oopsies. We'll do 2, negative 2, 5. So you get negative 4, 10. Now, because it did not give me starting in terminal points, it did not give me the initial terminal, you can just decide wherever you want it to start. Where's a good place for these graphs to start? 0, 0. So if we have a vector that starts in 0, 0, and I think I might have, this probably was in there and I skipped over it. If we have a vector that starts at 0, 0, we're just saying that it's in the standard position. Because if I have a random vector floating through the air, it's a gravitational pull or something, I can just decide wherever I want my XY chart to be, because it's not like there's an XY chart involved in that. I just put it there so I have a way to quantitate where the number, like what the numbers are, and give it a scale. Okay. So here I've got vector V, which is negative 2, up 5. We multiplied it, and we ended up at negative 4, up 10. So vector 2V is the whole thing. Any questions about that? The next is W minus V. So W is 3, 4 in component form. Take away V, which is negative 2, 5. So we're going to subtract each of those. We'll get 5, negative 1. So if I start 3, 4 in the origin, at the origin, so I'm going to go 3 right, up 4. Then here's vector W. Then to the end of vector W, we're going to do subtract negative 2, 5. So we're really adding 2, subtracting 5. So for my minus V, I'm adding 2 and then subtracting 5. So that's vector minus V. That gets added on to the end of W. Our answer is the vector 5, negative 1. And on this graph, we can see that from 0, 0, if I just drew straight there, that vector, that was terrible, would end right at. So I accidentally stopped the recording and didn't record C. You can pause it and look at the work and look at the graph. We also went over the properties. Now we are on unit vector. So we talked about unit vector on a different page. Unit vector is a vector that has a length or a magnitude of 1.
Hey, he's trying to show me something on my back. I don't know what. Be honest.
Okay. If I want to find a unit vector, I could take the regular vector V and divide by, what do these symbols mean? That means the magnitude. Should I zoom in? It's not a pi. That means the magnitude of v. So if I take the vector v and I divide by the magnitude of v, I will get a unit vector. Another way we could think about that is if 1 over the magnitude of v, instead of dividing by a number, we multiply by its reciprocal. Now it's a scalar. So that would mean I would distribute into the components in component form to find the unit vector. So we're going to find the unit vector in the direction of vector v, -2, 5, and verify that the result has a magnitude of 1. So it says to do that, we need to find the magnitude. So the magnitude of v is taking the difference of the x's, difference of the y's, which we already have, -2 squared plus 5 squared, and doing Pythagorean theorem with it. And I get 29, square root of 29. So that is the magnitude of v. That's how long vector v is. So then we're going to do 1 over square root 29, which is 1 over the magnitude, and multiply that by -2, 5. I didn't need that parenthesis. So we will get -2 over square root 29, comma 5 over square root 29. Don't worry about rationalizing it right now. We all know how to rationalize with just a radical by itself down there. Easy stuff. We're not going to do it right now. Okay. So this should be the unit vector. We'll call it U. It doesn't really say what to call it, but we'll call it U because unit. Now we have to verify that that really is 1 unit long. So to find how long it is, what do I do? To find how long it is, what do I do? Hint, we found how long vector v was just a moment ago. So how do I find how long vector u is? I can't hear you. The distance formula. I find the starts with an M. Magnitude. We are just like using that new vocabulary. So we're going to find the magnitude of u, which is the distance formula. And the x component, the change in the x's, is -2 over square root 29. So I'm going to take that and square it. Plus the component for the y's and square it. So I will get 4 over 29 plus 25 over 29, which is the square root of 1, which is a magnitude of 1. So there we are able to verify, you like how I put those words together? Verify that the unit vector is actually 1 unit long. So if we need to take a vector and change it into a unit vector, that's how we can do it. So component form. Oh yes, I'm sorry. Go ahead.
So it says verify that it has a magnitude of 1. Could it be possible that it would say have a magnitude of 2 instead?
No, not the unit vector.
Okay.
If you were verifying some other vector has a result, a magnitude of 2, sure. You just have to do the word for it. But the unit vector has to be 1 unit. Yeah. And hopefully you don't make any mistakes when you're finding your unit. Like this is the purple part is finding the unit vector. The pink part is basically checking our answer. Okay. Now, there are 2 unit vectors that are important, and we use these unit vectors to write vectors in a completely different form. And this is where last year some students had trouble because they didn't learn the vocabulary. So component form is what we've been doing so far. Component form is like the change in the x's, which they called v1, and the change in the y's, which they called v2. That's component form. But the next one is going to be called, I'll get there in a second. It's not right here. So we're going to start with some standard unit vectors, and we call those vectors vector I and vector j, and they're like always called I and j. That's like a standard thing. And those vectors are 1, 0 or 0, 1. So if I were starting at 0, 0, which this picture is actually there, I just like doing it from scratch so you can see me doing it. If I were to represent vector I would start at 0, 0, and I would go 1 on the left, not on the left, on the x, and I would stop, and I would go nothing on the y. So that's vector I. If I want to represent vector j with 0, 1, I would start at 0, 0, or wherever I decide to start. And I would go 0 x's and up 1 on the y. So that would be vector j. Those are two different vectors. One of them, we've got component only on the x, and it's 1. So it's kind of like a parent function type thing. It's like the most generic one ever. And then the other one, we've only have the 1 on the y. It says, note that lowercase letter I is written in boldface to distinguish it from the imaginary I, which I always write in cursive. So if I write an I, because I can't really write so much in boldface, if I write an imaginary, if I write an imaginary I, you guys will see me like do that, because I is the vector I. They just had to use the same letters for everything, whoever made this stuff up. Now, we can take any vector at all, and we can take the component form v1, v2, any vector at all, and we can rewrite it, and this is called linear, combination. There, this is called the linear combination. It's written down below, but this is called a linear combination. It's called a linear combination when we have the I and the j. If we have it in the chevrons, it's called component form. If we have the I and the j, linear combination. I'm going to take a vector and just do what they did so you guys could see it happening. Somebody give me an x component, any. 4. Okay, give me a y component. I heard -7. So if we take 4 and we multiply it by I, which is 1, 0, plus we take -7 and we multiply it by j, which is 0, 1, I'm going to distribute that. I'm going to get 4, 0, plus distribute this, and I get 0, -7. Before I go any further, why am I allowed to distribute that? Yeah. It's not the distributive property, because I'm not, okay, so I'm saying distribute, but I'm not really distributing. It looks like I am, but I'm not really using the distributive property. This showed up earlier in our notes. Do we forget? It's scalar multiplication. So that's scalar multiplication. 4 is a scalar on a unit vector. So I'm basically taking that vector and making it longer. Same direction, just longer. Same thing with the -7, only this one I'm switching the direction because it was positive, now I'm going negative. Then when I add these together, remember to add vectors, we add the x components together, so we get 4. And then we add the y components together and we get -7. So this is totally component form. Now what they're saying is this is I and this here is j. So another way of writing this vector in linear combination form would just be to write that 4 next to I, and I'm going to write minus, but it would be like plus -7 next to j. So you don't have to do all the steps in between because we just did it and see how it works. You can go from here all the way to there. So there's me switching from component form to linear combination form. Yes?
Like on tests and stuff, would you want us to do like plus minus or just the minus?
Oh, minus. I'm just saying like we're adding the j, but really it ends up being subtraction. So we all know it's not really subtraction. Okay. All right. writing a combination of unit vectors. So let u be the vector with an initial point at 2, -5 and a terminal point at -1, 3. We're going to write u as a linear combination of the standard vectors of I and j. So I'm going to start in component form. I guess you don't even have to do component form at all, but I always like to use it. And I'm going to do -1 minus 2 and 3 minus -5. So I get -3, 8. Questions about what I did? Now it says we're going to take that and write it as a linear combination. So we're just writing it in a different form. Looks different, but it's the same thing. Represents the exact same thing. What do I do? So we're going to write -3i plus 8j. Done. We're just switching between forms and that's it. It might seem confusing, like, because you've never used it before, but that's really all you have to do to switch. Yes, Ria?
So you did -1 plus -2, right? But how would you not know not to do the other way around again?
How do I know not to do 2 minus -1? Because of the words initial point and terminal point, I have to start with the terminal and subtract the initial. We always do this. Remember, like x2 minus x1, like with all those other formulas. Other questions? Somebody else will say, yeah, Caitlin?
So if it doesn't like specify which one's the initial, which one's the terminal, if there's a picture and there's an arrow, the arrow goes away from the initial. Right.
It's the direction it's going. So it would point away from the initial because we're going to the terminal. Yeah.
Is this a function of a graph? Or like
It is a vector. That is a vector. It's just in a completely different form. What? Can you graph a vector on your calculator? I don't know. I don't think so. I don't know. Let me get back to you on that. We can Google that. Okay. All right, so here's vector operations. We're asked to find 2u minus 3v, and we've got 3i plus j, and v is 2i minus j. You don't have to take it and put it into component form and find the answer and then put it back. You can leave it in linear combination, and we can do 2 times -3i plus 8j minus 3 times 2i minus j. We just like leave it in that form. And then combine like terms. -12i plus 19j. And that's the linear combination form for that vector. What would be the component form answer? -12, 19. Don't overthink it. That's the component form. This is the linear combination. This is component. Okay? So far, vectors aren't too bad. So far. Now, I mentioned this earlier. You are going to find direction angles. Okay, you're going to go find those direction angles. Let me go and just, before I go, because I feel like the way that they worded it got really confusing just to read straight through it. And I feel like you guys can understand this better by me just making up a vector and let's talking for a moment. Okay, so let's say I have a vector and I will put, the vector can be anywhere, but I'm going to put it at 0, 0, so it's even easier for us. So I'm going to have my initial point at 0, 0. And let's say that I am going, that first page one was like 3 and then 2. I think that's what it was. And if I have it backwards, sorry, I'm not looking. So we're going from here to here. The component form of this would be 3, 2. Questions? Now, finding the directional angle is always going to go counterclockwise. the same way we did in the unit circle. We're going to start at that same initial side, the positive x-axis, and we're going to rotate counterclockwise. If I were to draw a triangle, I could find that angle using trigonometry. If I were to label my sides, this would be what side? How long? 3, and then 2. What trigonometric ratio could I use to find that angle? Tangent. Tangent, and we'll call that angle theta. Tangent of theta is 2/3, which is the same as what from the front page? Right. Tangent is the change of the y's of the change of the x's. So tangent is the slope of that line. Did you know that? I feel like it was in something somewhere, but maybe for like a half a second. What? Tangent is y over x. Yeah, which is y over x. Yep. Yep. All right. Now what we were trying to find the angle. So how do I find the angle for this? Is it one that I recognize from our unit circle? No. So how do I find it? Inverse tangent, right? So we'll have theta equals, you could do arctan or you could do tangent inverse, 2/3. How do I actually find a number? Yeah, calculator. You just have to, if you need a number, which we're going to find numbers, we're not going to leave it as arctan 2/3. If you need a number, we're just type it in our calculator, okay? Here, I got a calculator somewhere. Somewhere I got one. So yeah, if you want to grab out your calculator, we are going to use it for a couple questions. And then we're in degree mode. I think it's going to keep switching here and there while we do vectors, but it's going to start today in degree mode, just, so you can be in the right mode. So I've got second tangent 2/3, and that would be a 33.69 degree angle. If we wanted the radian, then we just switch modes. Okay? So that's directional angle. Now, here we're going to break the unit vector down and look at different forms of the unit vector, which is going to be used a lot going forward. So we just found the directional angle, and I feel like with no problem. Like once I was guiding you through it, you're like, oh, that makes sense. We've done that a bazillion times. So this looks different, but it's not really hard. You just take a little bit of getting used to. So our unit vector is going to be xy. The length of it is 1. All right. Because we know that x is cosine and y is sine, we can say that the unit vector is also cosine theta, comma, sine theta. In the unit circle, the x is the cosine, the sine is the y, right? So we can just rewrite it that way. We can also take it and write it in linear combination. So cosine theta I plus sine theta j. So remember, these are just the exact same things. This is just a component form. And then this is linear combination. But they're the exact same thing. Now, if it's not a unit vector, then what we have is we have a scalar on the unit vector to make that particular vector. So every single vector we can write as a unit vector like we did back here. Every single vector, where is it? Every single vector, we could write it as a unit vector like this one right here, this U. Let me do it in a different color, this U. And then if I take that unit vector and I multiply it by the magnitude of V, what do I get? I get negative 2, 5, which is what in this example? Can't hear you. What is negative 2, 5 from this example? What is negative 2, 5? It's that original vector. So what we did was we wrote the unit vector U, but if I take the magnitude of V and I'll multiply it back through, I now go back to V. So we like divided by the magnitude of V, now multiplying by the magnitude of V, okay? So in this example, we've already divided out the magnitude of V, and that's how we have a unit vector here. So we've already divided out that magnitude of V, and we have a unit vector. So what they're doing is they're putting it back in, they're multiplying it back in so that we have vector V. So vector V, instead of writing it like x comma y, they're writing it with the cosine and sine because we're using the unit vector. So vector V, we would have the magnitude multiplied by the cosine of I plus the magnitude multiplied by the sine of j when we put it into linear combination. So we've got component form, and then we've got linear combination. Now here they're saying because vector V is equal to AI plus BJ, A representing like on that one we were just talking about, negative 2, 5, where you do negative 2I plus 5J, because vector V would be some number times I plus some number times J, then we can use our quotient identity and we can do sine over cosine, multiply that by the vector, not vector, the magnitude of vector V, and simplify that to get B over A. That is what we did here without all of that vocabulary and special symbols. Our B in this case was 2. Our A was 3. We put them on top of each other. We did tangent inverse. That's what we did. But on that other page, it just looks so complicated. But we do need to go through this because we are going to be using these formulas a lot. Okay, so we do need to understand where the formulas are coming from. So now, find the direction angle of the vector. We're going to look at vector U. This is not a unit vector. It's just a random U. Maybe we'll make a W and it won't be as confusing. Can't even tell. So this is just some random U or W vector. There we go. So what would be our A value? 3, and our B value is 3. And what they're saying above is that's the same thing as this is cosine theta times the magnitude of V. That's what A is. And the magnitude of V times sine theta is this answer. But to find the angle, we need to use tangent. So we're going to do tangent of theta is equal to B over A. Tangent of theta is equal to 3 over 3. Tangent of theta is equal to 1. What's theta? Okay, so I'm hearing 2 answers, but we do not know where the terminal or initial point and terminal point are. All we know is direction and magnitude. we know that when I write it, if I wrote it into component form, 3, 3, I know that from start point to end point, we are going 3 to the right and 3 up. So I know that it can't be 5 pi over 4 because that would have a left and a down. That would be -3, -3 from standard position. Okay. So this one I know is pi over 4 or 45 degrees, depending on whatever they want their answer to be in. And I think they changed it. I remember asking, like, why is this answer in degrees and this answer is in radians? Does it matter? And the answer was no. It's just they changed it up. So last example. Oh, we got like 3 minutes. We used a lot of time in here. The game was too fun. So tangent, we're going to do -4 over 3. So that's going to put us in what quadrant? Three, down 4. Those of you saying second, you were going in the order of -4, 3, but that's the y's over the x's for tangent. We need to find the angle. This one we don't know, so we're going to have to use tangent inverse. And on my calculator, on our calculator, it's going to give us -53.13, but we have a problem. That is because of the restrictions that your calculator follows. But with vectors, we start at 0 and we go counterclockwise. So it's not going to be -53.13. With vectors, we start at 0, we go counterclockwise. So what do I do to this number? Add 360, or if it was in the other form, 2 pi. What's the answer to this one? 3 something, right? 306.87. So that would be the directional angle. That would be what theta is for this. So you guys, if you have questions on law of sines, law of cosines, and you want to hang out for a moment, I can answer questions. You can also send me emails. We've got law of cosines, law of sines quiz tomorrow. This assignment is due Monday night. So if you have questions on this, you can wait to ask. Or if you just got to know now, you can ask now.